In this video here, we're going to take a look at modeling with first order differential equations. Now we can use first order differential equations to model real life problems, with one example being kinematics. And you should have covered some of these concepts back in A-Level Maths, and as such be aware of the relationship then between displacement, velocity and acceleration, as we can see here. So v, the velocity, is equal to the derivative of the displacement s with respect to time t, and the acceleration a here is equal to the derivative of the velocity v, again with respect to time t. And I've already mentioned it here, but s is the displacement, v is the velocity, and a is the acceleration at time t. Now we can use these relationships to form first order differential equations, which we can go on to solve either by using the standard methods of integration and separation of variables, as we saw in A-Level Maths, or by using an integrating factor, as we saw in the previous chapter on differential equations. And we can also use first order differential equations to model real life situations involving rates of change. So don't be surprised here if you see an example based on water going into a container and water coming out of a container. It's a very, very common example here that involves rates of change. And then finally here, exam questions on this topic will often ask you to show how a given differential equation has been constructed. And this is something that students do struggle with to begin with. There isn't really a magic trick to kind of get better at this. The only thing you can really do is just keep practicing these types of questions. Okay. Well, that concludes this introduction here to modeling with first order differential equations. We're not really introducing anything new here. It's just building on everything that we've seen for differential equations in A-Level Maths and everything that we've seen so far from Core Pure. So let's just work through one practice question here for modeling with first order differential equations. So let's just have a go then at this practice question here. So for this question, we're told that initially a storage tank contains 500 litres of water. Liquid is removed from the tank at a rate of 20 litres per hour, and a chemical solution is added to the tank at a rate of 25 litres per hour. The chemical solution contains 2 grams of copper sulfate per litre of water. We're then told that it's assumed that the sulfate disperses throughout the tank on entry. It then says, given that there are x grams of copper sulfate in the tank after t hours, show that dx by dt is equal to 50 minus 4x all over 100 plus t. So for this question here, or certainly the first part anyway, what we want to do here is show how to construct this differential equation, right? And I did mention that in the introduction that sometimes you might be required to show the construction of a differential equation. So for the first part of this question in part A, that's what we want to demonstrate here. So to get us started then with part A here, all I'm going to do is take all of this context here and turn this into something useful mathematically. Okay, so for part A then, let's just make a note here. The easiest place to begin with here is to consider the litres of liquid in the tank after t hours. So let's just make a note of that here. So litres of liquid. So litres of liquid in the tank after t hours. Okay. So what are we given here for this question? Well, we're told that initially the tank contains 500 litres of water. So we have 500. What else are we given here? We're told that liquid is removed from the tank at a rate of 20 litres per hour. So I've got 500 minus 20t, because it's per hour, right? So after t hours, 500 minus 20t. And we're also told that a chemical solution is added to the tank at a rate of 25 litres per hour. So we also have plus 25t. Okay. So if we simplify this here then, what we get is 500 plus 5t. Like so there. Okay. So moving on then, we're now going to consider the copper sulfate in the tank. So we're told that there are x grams of copper sulfate in the tank after t hours. So what we want to know then, or what we want to consider here, is the concentration of copper sulfate after t hours. So again, let's just make a note here. So for the concentration, of copper sulfate after t hours again. Okay. So for the concentration of copper sulfate after T hours here, this would be given by X grams of copper sulfate in the tank after T hours divided by the litres of liquid in the tank after T hours. So altogether then what I've got here is X all over 500 plus 5T. So 500 plus 5T. Okay. So we're getting pretty close now to the constructed differential equation here. It might not quite look like it at this point, but I promise you we are getting close. The only thing left to really consider here now is dx by dt. So given that there are X grams of copper sulfate in the tank after T hours, what that means then is dx by dt here is simply just the rate of change for the copper sulfate, of course, with respect to time t. So dx by dt here, so dx by dt would simply be the rate in, so rate in minus the rate out. Okay, like so. So in this case here, this would just give us the rate of change for the copper sulfate. So let's just keep going here. So in that case then, the rate in for the copper sulfate, so rate in for, I'm just going to shorten this to CS here or abbreviate it to CS here. CS just meaning copper sulfate. What I'm going to get here then, oops, didn't mean to do that, just ignore that, is 25, because we have the chemical solution going into the tank at a rate of 25 litres per hour. That's 25 times by the grams of copper sulfate per litre of water, which we're told here is 2 grams of copper sulfate per litre of water. So I've got 25 times by 2, which would give us 50, of course, like so. And now for the rate out for the copper sulfate, again, let's just do this underneath here. So rate out, again, for CS here, just meaning copper sulfate. This is given us then. So the liquid is removed from the tank at a rate of 20 litres per hour. So I get 20 times by the concentration here of the copper sulfate. Okay, so it's going to be 20 times by this expression here. So 20 times by X all over 500 plus by T there. Okay, like so. Which obviously, if I just simplify this here then, this would give me 20x. I get 20x all over 500 plus 5t, like so. Then obviously, if I just divide top and bottom by 5 here, in that case, I get 4x. We get 4x all over 100 plus t there. Okay. So altogether then, so we're pretty much done here then with part A. So for dx by dt here, as we've already mentioned, right, this is just the rate in minus the rate out. So the rate in here is 50. We get 50 here minus the rate out, which is 4x over 100 plus t. So I get 50 minus 4x all over 100 plus t there, like so. And as you can see then, exactly as required. So as required there, like so. And there we have it. So that gives us the solution to part A. Now, as you can see, we have already took up the full screen here just to answer part A, right? So clearly what I'm going to need to do here is just quickly pause the video, clear the screen, and then we can have a go at answering part B. So for part B, then it just says, hence find the number of grams of copper sulfate in the tank after 4 hours. So for part B, then all we need to do here is solve this differential equation and obtain our general solution. And all we need to do then is just substitute t equals 4 into the general solution to find the number of grams of copper sulfate in the tank after 4 hours. Now in its current form here, you might not recognize how to solve this, but by adding 4x all over 100 plus t to both sides, we get it into a form that's more recognizable. So for part B then, as we've just said, right, let's just add 4x all over 100 plus t to both sides here. I get dx by dt plus 4x all over 100 plus t, and this is equal to 50. Okay, so to solve this differential equation here, what we need to do is use an integrating factor. So for the integrating factor here, so I'm just going to abbreviate this to I dot f here. This will be equal to e to the power, so it's e to the power then of the integral of p of t, that's going to be this here, so p of t with respect to t, which in this case is e to the power of the integral of 4x all over 100 plus t with respect to t. We get 4x all over 100 plus t with respect to t. Okay. So if we integrate this here, then what do we get? Well, nice and straightforward then. So this integral here would give us 4 ln 100 plus t. We get e to the power of 4 ln 100 plus t. We can now just use the power rule for logarithms here. We get e to the power of ln 100 plus t power of 4, like so. And given that e and ln are the inverse of each other, this just cancels to give us 100 plus t. So 100 plus t to the power of 4. Okay, so this here then is our integrating factor. So once we obtain the integrating factor here, what we do then is we take the original equation and times through by the integrating factor. So in that case, then what I get here is 100 plus t to the power of 4 times by dx by dt times by dx by dt. I've then got 4x all over 100 plus t. So given that I'm timing through by 100 plus t to the power of 4, one of those 100 plus t's will just cancel. So I get 100 plus t to the power of 3 times by 4x there. So 100 plus t power of 3 times by 4x. And then in this case here, this will be equal to 50. That's equal to 50 times by 100 plus t to the power of 4. Okay. So at this point here then, probably one of the trickiest things to note is the left-hand side is equal to d by dt of, so I get 100 plus t to the power of 4x. So let me just write that down. 100 plus t to the power of 4 times by x, like so. And this is equal to 50 times by 100 plus t to the power of 4. Okay. So d by dt here of 100 plus t to the power of 4 times by x, what we now do is we integrate both sides here. So given that this is a derivative, if we integrate a derivative, they just cancel, right? So I get left with the argument here, this 100 plus t to the power of 4 times by x. I get 100 plus t power of 4 times by x is equal to, so again, all I need to do here is integrate the right-hand side. Nice and straightforward, just add 1 to the power, divide by the new power. So altogether then we get 10, because we divided by 5 here, so 10 times by 100 plus t to the power of 5. And don't forget here then the constant of integration, right? So plus c, like so. And what I'm going to do here then is just make x the subject, right? That would give us the general solution here. So to obtain the general solution here then, just divide through by 100 plus t to the power of 4. So x is equal to, so we get 10 times by 100 plus t. So 10 times 100 plus t. Then we have c all over 100 plus t to the power of 4. So 100 plus t to the power of 4. Okay. So to now go on to find the value of c here, what we need to do is use an initial or boundary condition, right? Now, by looking at the question here, it might not be immediately obvious what the boundary condition actually is. But what we can do is use the fact that when t equals 0, so when t equals 0, the tank initially just contains litres of water, right? 500 litres of water. There is no grams of copper sulfate in the tank. When t equals 0, x is also equal to 0, okay? And by using this initial condition here, we can now go on to find the value of c, okay? So if I substitute t equals 0 into this equation here, I get 10 times 100 plus c all over 100 to the power of 4. But obviously we want to find the value of c, right? So what I'm going to do here is just make C the subject. So subtract this off both sides and times through by 100 to the power of 4. So what we get here then for C is that C is equal to, I'm going to get minus 10 times 100. And we then times this by 100 to the power of 4. In other words, it's just minus 10 times 100 to the power of 5, right? Which, if we evaluate here, just gives us minus 1 times 10 to the power of 11. Okay? So now that we have the value of C here, we can now go on to find the number of grams of copper sulfate in the tank after 4 hours. So when T equals 4 then. So when T equals 4 here, what do we get? So in that case then, X, the number of grams of copper sulfate, is equal to, so X is equal to 10 times by 100 plus 4. That's going to be 104, right? Plus C, which is minus 1 times 10 to the power 11. So plus minus 1 times 10 to the power 11 all over 100 plus T to the power of 4. So T is 4 again. So 104 to the power of 4, like so. Obviously, at this point here, just put this into your calculator. And if you do this correctly here, then just obviously give your answer to a sensible degree of accuracy here. I'm going to round it to 3 significant figures. What we get here then is 185 grams. So 185 grams there. And there we have it. So that gives us the solution to part B. And that gives us the solution then to the one practice question for this video. And that actually brings us to the end then of this video here on modeling with first order differential equations.